Hi there, welcome to this video. A few years ago I modeled a Tesla Model S in SolidWorks. I just did it for fun to improve my surfacing skills in the software, and over the years I got a few questions about performing some computational fluid dynamics on the model. So CFD is something that I don't really do at my work. I do mechanical design, but I've never really had the need to perform any CFD. So I thought it would be an interesting thing to do. And I got some cool results, so I thought I'd make a short video to share it. And this video will also sort of be like a tutorial if you're interested in performing any computational fluid dynamics in SolidWorks. This will show you how to set it up in the software. So I'll go through some of these results later, but for now I'll just delete this study and run through it again. So just back to the base model, a few things to mention off the bat is that this is a single solid body model. So what I mean by that is everything's just one solid unit. Obviously a real car consists of many bodies joined together. So for example, you'll have a door panel next to the rest of the body, and you'll have little gaps in between. In this, everything's just solid, so keep in mind that will affect the results slightly. And just keep in mind that this is an approximation of the actual real Tesla Model S. I made this using blueprints, and yeah, there's going to be some slight differences between this and the real model. Also, I designed this to be 3D printed, so I knew on like a small scale, for some of the details to be visible, I would need to do certain things like here on the windows, I've extruded out some edges, and this front window, it's actually slightly recessed in. So I did that just so these details stood out in the small scale 3D print. Also, when I was setting this up for the simulation, I brought in the wheels and I had the body and the wheels as an assembly, but that was giving me problems. So I just combined everything into a single solid part file and ran the simulation on a single solid body, and that seemed to work. So I'll just talk a little bit about drag, because one interesting thing to look at in this simulation is the drag coefficient. So the drag coefficient gives an idea of how efficiently an object will move through a fluid, and it's governed by this formula down here. So we have the drag force, which it says by definition is the force component in the direction of flow, and then divided by the mass density of the fluid, multiplied by the flow speed squared, and multiplied by the reference area. So in our case, the drag force is something that we can find from our simulation. The mass density of the fluid in our case will be using air, obviously, because the vehicle is driving through air. So we can just look that up. And the reference area, so I'll just explain the reference area. The reference area would be the frontal projected area. So if you're looking at the car like this, it would be all of the frontal area you can see that would be projected onto this front plane of reference. So ideally, to get that in SolidWorks, you would just use the evaluate tool and hit measure, and come in and measure all your surfaces, and it gives you the total area. But the problem with this is it's actually giving you the total three-dimensional area of the surfaces. It's not giving you the projected frontal area. So the easiest way I found to actually get an estimate for that area is by realizing that if we took a cross-section halfway through this car, the cross-sectional area would be a rough approximation of that projected frontal area, which I think is good enough just for this rough simulation I'm doing. So to do that, I'm just going to do a sketch on this front plane. I'll just draw any kind of object that encompasses the shape and do an extruded cut through everything. So now I can come in and measure this surface, which gives this value here in millimeters squared, and I just converted that to square meters previously, and it gives about 2.2 square meters. So just make sure that Just make sure that when you are getting numbers like this, they do make sense. In this case, 2.2 square meters does make sense for the cross-sectional area because the car is approximately 2 meters wide by 1 meter tall, roughly. Yeah, it's just good to double check that the values you're getting make sense as you're going along, just to make sure you're not making any kind of mistake. Okay, so to jump into the flow simulation, you want to have flow analysis installed in SolidWorks. It's an additional add-on. So I'm going to go to the flow simulation ribbon and I'm going to hit wizard, which is going to allow me to create a new project. So I'm just going to hit next. I'm going to select SI units and hit next. So now we're doing an external analysis type because we have fluid flowing around an object, as opposed to an internal one where you might have, water flowing in a pipe, for example. I'm going to exclude cavities without flow and exclude internal space. There shouldn't be any internal space in this model, but I'll just exclude that just in case. And gravity we want turned on. So important to note, the default direction of the gravity vector is acting along the z-axis. In our case, we actually want that to be acting along the y-axis in the negative direction. So I'm just going to delete this and make that 0. And then in the y-axis, make it negative 9.81 meters per second squared. And hit next. So the fluid that we're looking at is air, obviously. So I'm going to add that in. Surface roughness, I'm not going to worry about too much for now. And this is an important step. So we want to add our velocity. So the car will be driving forwards, obviously, which means that our relative fluid flow is in the Z direction, rather in the negative Z direction. So I'm going to come in here and input negative 30 meters per second. I'll explain a bit later where I got this 30 meters per second from. And yeah, it's important to make sure that it's a negative, otherwise it will be coming over the back of the car, and if you're on your simulation, it will just be a big waste of time, and that's definitely not a mistake that I previously made. So I'm going to hit finish. Okay, so this gives us a computational domain. So I'm just going to adjust this a little bit. I'm going to bring the base up to the height of the wheels, and I'm going to bring the edges of the bounding box in a little bit. I don't want to bring them in too close because, as we know from Bernoulli's law, if fluid is compressed into an area, then it will accelerate. So if we're bringing this like artificial wall in too close, yeah, it's going to affect the sort of fluid dynamics around it. So I'm going to leave a fair amount of space around that. And I'll just adjust it in this direction as well. Okay, that looks reasonable to me. So I'm going to right click on the goals here and insert some global goals. And we get a big list of parameters that we can look at. So I'm going to look at the velocity, the maximum velocity. We could look at the velocity in the different components as well. I'm also going to look at the maximum force in the different components as well. The force in the Z direction is actually very important here because that is our drag force, and we'll need that to compute the drag coefficient. I might also just look at the friction force out of interest, and I think that's enough. We can look at other things like volume flow rate, mass flow rate, but yeah, I'll look at the pressure as well. Okay, so I'm going to hit OK. So now, because this is a finite element analysis, we need to create a mesh, or at least set the parameters of that mesh. So I'm going to right click and go into the global mesh settings. I'm going to set the resolution of this mesh quite high because I know that will give more accurate results. The trade-off is that the analysis will take longer to run, but that's not a big problem for me now. So yeah, I'm just going to leave it on automatic and hit OK. And yeah, as I was previously talking about the drag coefficient before, that is something that we do want to look at, because it's kind of like a standard value that you can use to compare to, say, other automobiles. So yeah, if we look at automobile drag coefficients, we have different numbers for all different types of cars. Original Volkswagen Beetle was 0.48. A more modern car like Subaru Forester, 0.38 kind of thing. So I think a Tesla Model S is about 0.2 to 0.25. I think the older models are about 0.25, and yeah, the newer Plaid versions are 0.2. So I'm not expecting this to have such a low drag coefficient, because yeah, as I said previously, this is an approximation. I just like modeled this relatively roughly. Also, some sections like here, these front grills, they're just solid, but you know, in the real version, these would allow some airflow through, and yeah, there would be different like optimizations to bring that drag coefficient down. But as long as this gets relatively close to the actual theoretical value, I'll be happy with that. So yeah, we can't actually directly measure the drag coefficient, but what we can do is right click on goals and insert an equation goal. So this is our equation here. So we're going to put 2 multiplied by our drag force, which is the force in the Z direction, divided by the mass density of the fluid. So that was 1.225, I believe, I just double checked that. Yeah, 1.225 kilograms per meter cubed for air. Multiplied by the flow rate, so 30 meters per second squared. I'll just explain actually where I got that 30 from. So obviously, looking at this formula, we know that the flow speed, it affects the drag coefficient, and it's kind of like an arbitrary value we're choosing. So in Australia, where I live, the maximum speed you can drive a car on the highway is about 110 kilometers per hour. So converting that to meters per second gives 30.5 meters per second. And it makes sense to me that, yeah, you would be more interested in the drag coefficient at higher speeds. There'd be no real point looking at it for low speeds. But yeah, this list of automobile drag coefficients on Wikipedia, it doesn't actually specify what flow speed is used in these calculations. My understanding, I would assume that manufacturers do use some kind of standard. But yeah, if you know more about that, let me know in the comments. And yeah, if you have more experience with computational fluid dynamics in general, please share your thoughts. As I said in the beginning, this isn't anything I'm an expert in by any means. So yeah, finally we'll just multiply the denominator by the reference area. So the reference area that we calculated earlier was approximately 2.2 square meters. And just one point of note, this will actually give a negative value because our force is being calculated in the direction pointing away from the car. So if I just make this whole numerator negative, multiplying it by -1, that will give a positive value. So I'm going to hit OK. So I believe that is all ready to run now. So I'm just going to hit run. And yeah, this will take a little bit of time for the computer to solve, depending on your computer's specs. But because I have set the mesh as quite fine in this case, it will take a little bit of time. So I'm just gonna let this run for 10-15 minutes, however long it comes, and resume the video when it's done. Alright, so the solver looks like it's finished. I've been away for a little while. So first thing we can do is come in here and expand the results section. So I'm going to add in a flow trajectory, and that's going to allow us to visualize the airflow over the car. So I'm just going to increase the number of points, and I'm going to select a predefined plane, and we want to visualize the velocity here. So hit OK. And I can right click and animate that. So yeah, this is a pretty interesting thing. We can see the arrows representing the airflow moving over the car. As we see it hit the front, it's sort of slowing down as expected. And interestingly, we can kind of see that the air is accelerating or moving faster as it goes over the top. So I think this actually might be due to what I was mentioning previously, where we have this upper bounding ceiling of the computational domain, and that forces the fluid to be compressed in this area, and therefore it must accelerate, as we know from Bernoulli's principle. So I'm not sure if that's actually totally accurate. I think if this ceiling was higher, we might not get that. But it could also be sort of just acting like an aerofoil shape and accelerating the fluid over the top. If you know a bit more about that, feel free to comment below. We can also see the air sort of slowing down at the back as it exits, some of these more green turquoise colored arrows. So to actually get a better picture of that, I can insert a cut plot. So I'm going to do that on the right plane. And I'm going to look at streamlines for velocity. Yep. So I'll just actually hide the trajectory now to make everything a bit clearer. So yeah, as before, we can see as the air comes in, it's essentially hitting a flat surface here, which is slowing down the flow speed, and we even seem to be getting some vortices at the front there. And we do see an area of increased flow speed above the car, and at the back are like some large vortices and greatly decreased flow speed. Even looks like it's even close to 0 meters per second. So the nominal speed of the 30 meters per second is this kind of like yellowy color, which we can see for the most part. And then the orange and red is 34 up to 38 meters per second. So yeah, I'm not sure if that's completely accurate, but interesting nonetheless. So I'll just hide that. We can also look at a surface plot. So I'll do a surface plot of the pressure. I'll select all surfaces. And this kind of shows the pressure is increasing at the front of the car because we've got a direct stream of fluid coming in, and area of decreased pressure at the top of the car. So that indicates some lift essentially. So that's similar to how like an airplane wing would be. It's actually interesting, like if you were to look at like the computational fluid dynamics on a Formula 1 car. Formula 1 car, you actually want to generate a lot of downforce. So it would be quite a different analysis looking at that. Just as a side note, I did notice that back in this automobile drag coefficient lift, Formula 1 cars have a drag coefficient of 0.7 to 1, so they actually have quite a lot of drag force, but I guess in their case it's needed because you need a lot of downwards force to keep the actual car on the track and not just flying off. So I'm just going to hide that. So there are a few other things you could look at, but they're sort of the main basic ones. Now let's look at the actual drag force. So if I go into the goal plot and insert, so the drag force we know was the force in the Z direction. So if I hit show, it shows a value of about 436 newtons. And we actually set up the equation goal previously to use that value to calculate the drag coefficient. So if I hit show, it's giving a average drag coefficient of 0.36. So I think that's reasonable. That kind of makes sense to me. It seems to be in line with a kind of typical car. If I search drag coefficient of a Tesla Model S, yeah, it's saying 0.28, whatever, first result this is. But I believe that's, the latest Model S played. This model I made was from 2017 or 16. It was quite a while back. And yeah, as I mentioned before, this is like an approximation. It's not a 100% accurate model, so I wouldn't expect it to be spot on. But yeah, that like 0.36 actually seems quite reasonable. Interestingly, so if I put in the friction force, so I'm going to look at the friction force in the Z direction. Yeah, so the friction force in the Z direction is only about 30 newtons. And so just coming back to this drag coefficient PDF, if we go down the bottom here, let me just find it. Yeah, it's explaining here that the drag force on a body could be divided into two components, namely frictional drag, viscous drag, and pressure drag. So, the drag is also obviously this force that's resisting the movement in the direction we're traveling. And this, since we calculated this friction force separately, and it's only 30 newtons, but the whole drag force is 430 newtons. To me, that suggests that most of the drag is coming from pressure differentiation, so like it's a pressure drag force. But actually, in saying that, I didn't properly set up the the surface like roughness parameters. So yeah, I'm not really sure like how accurate all this stuff is. It's more just of an overview. And if you do have more expertise in this area, please feel free to share your thoughts below. So yeah, that's pretty much everything I've got for you there today. If you have any questions, let me know. I did also model a Cybertruck in the past, so maybe I'll do a CFD of the Cybertruck and see how its drag coefficient compares to this Tesla Model S. And if you like this video, please consider subscribing and liking. And yeah, thanks for watching.